Good morning, dear students. Today we are going to discuss about the numerical problems of flywheel. Now we have to solve the one numerical problem in this lecture. This is the second numerical problem. We have solved the first numerical problem in the previous lecture. The problem is the turning movement diagram for the petrol engine is drawn to the following scale. That means scale is given for turning movement and crank angle. The turning movement diagram repeats itself at every half revolution of the engine, and the areas above and below the mean resisting torque line or mean turning movement line taken in order are 295 and so on in mm square. The rotating parts are equivalent to a mass of 36 kg at a radius of gyration of 150 mm. Determine the coefficient of fluctuation of speed, that means CS. We have to calculate the CS when the engine runs at 1800 rpm. So we will start the solution from the given data. So this is the given data. M is equals to 36 kg, radius of gyration 150 mm, then that means 0.15 meter, and speed n is equals to 1800 rpm, so that we can calculate the omega 2 pi n upon 60, that is equals to 188.52 radian per second. Now we have to draw the turning movement diagram because the areas above and below the mean turning movement line is given. Here you can see that the vertical ordinate represent the turning movement and horizontal ordinate represent the crank angle. And draw the mean torque line. This is the mean resisting torque line, and we have to show the all areas above and below the mean resisting torque line. So first area 295, then next one is 685, then next is given 40, then next 340, then 960, then 270, and after the 270 cycle repeat itself. Then you can represent the points, that is A, B, C, D, E, F and G, and area energy at point G, that is equals to energy at point A. So now here it is already given the turning moment scale 1 mm is equals to 5 Newton meter, and crank angle scale is 1 mm is equals to 1 degree, and in radian pi by 180 radian. Therefore, 1 mm square is equals to, that means 1 multiplied by 1, that is 1 mm square is equals to 5 into pi by 180. So 5 into pi by 180, that is equals to pi by 36 Newton meter. So in place of 1 mm square, that is equals to pi by 36 Newton meter. Let the total energy at point A in the turning movement diagram, that is equals to E. So we have to calculate energy at point B. This is the energy at point B plus 295, because the energy above the mean resisting torque line, and this is the energy above the mean resisting torque line minus energy below the mean torque line, that is equals to E minus K 390 at point D, E, F, G, and energy at point G, that is equals to energy at point A. And after that we have to identify which is the maximum energy and which is the minimum energy, and we can see that at which point energy is maximum or minimum. Here you can see that at point B maximum energy, and at point E this is minimum energy. You can see here, and we know that the maximum fluctuation of energy delta E is equals to maximum energy minus minimum energy. So this is the maximum energy minus minimum energy. So we can put the value of maximum and minimum energies in this equation. So we will get the value of delta E is equals to 985 mm square. But we know that the 1 mm square is equals to pi by 36 Newton meter. So substitute here. So this is the 985 into pi by 180. So after the calculation of this, we have the delta E is equals to 86 Newton meter. We also know that the maximum fluctuation of energy delta E is equals to I omega square CS, energy stored in a flywheel, and I is equals to mk square omega square CS delta E total. That is, here we can put the value of delta E is equals to 86 Newton meter, and M is also given, K is also given, omega we have already calculated 2 pi n by the 2 pi n upon 60, and only unknown is one, that is CS, coefficient of fluctuation of speed. We have to calculate this value CS, that is equal to 0.003 or 3%. This is the answer of this question, which is asked in question, coefficient of fluctuation of speed. So this is the final answer. Thank you very much.